In this video, I'm going to teach you about the half-life of a reactant. The half-life of a reactant is the time required for the concentration of, let's say, A to reach half its initial concentration. Okay, and so if the original concentration is A0, A at time 0, then the half-life is the time required for that concentration to drop to A0 divided by 2. That would be half the original concentration. So a lot of the time we'll use this type of symbols here. Concentration of A with the subscript 0, which means the initial concentration at time 0. But it's important to say from the beginning that this is kind of arbitrary. Even through the middle of a reaction, if you pick a particular point, you could call that the initial concentration and decide what half of that concentration is. But so there's a symbol for half-life, and it is T subscript 1/2. Okay, so that represents the amount of time required to reach half the initial concentration. So that has a very specific meaning. And it's found readily for the different orders of reactant by realizing that if you substitute in that value, the half-life value, you would get half the concentration. And so in a moment, I'm going to show you how I derived these, but the amount of time required to reach half the concentration, the half-life, for a first-order reaction can be shown to be the natural logarithm of 2 over the rate constant k. And it's approximately equal to 0.693 over k, because that's the value of the natural logarithm of 2. So if you just grab your calculator, type in the natural logarithm of 2, I guess I have to hit approximately equal. 0.693147 is what the natural logarithm of 2 is approximately equal to. Okay, so that's a really important result, and it's actually found on the equation pages that I've given you for the AP exam. If you can track those down, remember these pages that I gave you a while back, I've got them posted again here in my OneNote content library if you need another copy. And here you see in the kinetics section, it says T subscript 1/2 equals 0.693 divided by K. And I want to stress, for that particular half-life expression, that is only true, this one right here, that's only true for a first-order reaction, okay? So if we already know that the rate has that rate law, and the integrated rate law then is the natural logarithm of A minus KT plus natural logarithm of initial A concentration. If it's a first order reaction and these two equations hold true, then the half-life is the natural logarithm of 2 divided by K. Let me show you where that comes from. Okay, so off to the side here, I'm just going to show you the derivation for that. And so we start off with the integrated rate law for a first order equation, which we're learning is natural logarithm of A equals minus KT plus the natural logarithm of A initial. By the way, on your equation page, they've rearranged that slightly. They've subtracted natural logarithm of A initial from both sides. So it had been plus natural logarithm of A initial, and they've subtracted that from both sides, and they basically just moved it over here with the other natural logarithm. So they just rearranged the same equation that I've given you back here in the packet. It's the same equation I just wrote out, except they've moved this term over to the other side. Now here, I'm going to show you how you can derive half-life. We're going to substitute in the idea of half-life. All right. And so we're going to take that and substitute it. Oh, this is the wrong page, sorry. Here, we're going to substitute in half-life for the variable time. Time is a variable. Half-life is a specific amount of time. Okay, so even though we don't know what that is, we substitute in t subscript 1/2 for t. And if that's true, then automatically this other variable becomes defined as well. This entire thing becomes the natural logarithm of, parentheses, a initial divided by 2. Okay, so let's rewrite that with all of the things substituted in. The natural logarithm of half the initial concentration occurs at the half-life. And over here, this is still the constant, unchanged, okay? But we can rearrange this now. So now I'm going to subtract natural logarithm of a initial from both sides, kind of combine it, join it up over here with this other term. And so let me just kind of rewrite this a little bit here. We've got the natural logarithm of a initial over 2, and we're going to subtract out natural logarithm of a initial, and that equals negative k t half-life. Okay, and now what we can do is divide both sides by negative k. Okay, so if I divide both sides by negative k, I'm going to have a negative over here, and we can basically change the signs on everything. Another way to think about it is let's multiply both sides by -1 initially. So if I multiply both sides by -1, I'll give it this expression, and that becomes plus k t 1/2. And now I divide both sides by k. Actually, one more step before I do that. The way you can deal with logarithms if you're subtracting two different logarithms with the same base, you may remember in math class that you can represent that exact same type of thing by imagining those two arguments being divided by one another. Okay, so there's the first argument and then the second. Okay, so I've just restated these subtracted logarithms into one single logarithm, and that's still equal to kt half-life. And now we can simplify this down and divide both sides by k. You might notice that those initial concentrations would divide out, and we're left literally with the natural logarithm of 2, and we can divide by k, and that is t half-life. Okay, and so let me just give you an example of this first order half-life thing. In the reaction that we looked at a couple days ago, just depending on when you watch the video, we found that this was a first order reaction. Okay, and I've also written in another little comment here that you might want to pause the video and write this down. The rate constant k, you could find that from the slope of this line over here. It's negative 6.95 times 10 to the -3. Okay, so that's the rate constant. Okay, but I want to talk about the half-life of this particular reaction. And the half-life is actually pretty clear here in the data. Okay, so if you look just at the data here, the concentration data versus time, you can see that we've started off at time 0, 0.1 molar. Okay, so the half-life would be the time required to get to half of this original concentration. Half of 0.1 molar is 0.05 molar. Okay, so our concentration here has dropped by in half. It's been cut in half. So this here would be half of the original concentration. Okay, that is original concentration divided by 2. So what's the half-life then? How much time has elapsed for that to while that was occurring? 100 seconds. So 100 seconds seems to be the half-life. So what that means is every 100 seconds, we should see the concentration drop by 1/2. So let's see if that's true. After another 100 seconds, we can see that 0.05 drops by half again to 0.025. After another 100 seconds, we see that 0.025 is dropping by 0.0125. And again, after another 100 seconds, 0.0125 drops to 0.0062, which is about as close to a half as we could write it with 4 decimal places. Okay, so the half-life for this reaction is very clearly 100 seconds. Every 100 seconds, the concentration's being cut in half. Okay, so let me get rid of all those marks here. Now, that's clear from the data, but what we've just learned is there's another way that we could calculate this. For a first-order reaction, the half-life is equal to about 0.693, which is the natural logarithm of 2, divided by k. So let's see if that's also true. Since we know what k is from the slope of this line, it's the negative slope for this particular line, that's also a way we could figure it out. So we've seen that it's clearly 100 seconds by looking at the data, but let's also confirm that that equation I gave you a moment ago also works out. 0.693 divided by k. Now what in the world is k? Here it is, right there. Okay, so divided by 6.95 times 10 to the negative 3 per second is the unit. Okay, so let's type that into the calculator. We've got 0.693 divided by 6.95 times 10 to the negative 3. So numerically, here we can see 99.7. Okay, now remember this value right here was rounded to 3 significant figures. 99.7 is effectively the same as 100 seconds. Okay, what happens to the units then? 0.693, the natural logarithm of 2, doesn't have any units, and then we're dividing by the unit per seconds. So here, actually typing this in the calculator, we get half-life equals 99.7 seconds. Okay, and again, in terms of significant figures where we're rounding, you know, that's right on the money. Okay, so that's another way we could find the half-life. Let me see. I think that's the only first order one we have here in the packet. Let me go ahead and give you the results for the half-life for a second order and a zero order reaction. And I'm not going to derive these for you, but what I've done to find these expressions is following the same process that I did for the first order integrated rate law. I take I'll write it out a little bit. I take the second order integrated rate law, right? That's the expression. And I substitute in here, just like I did before, the half-life, the amount of time required to reach half the concentration. So over here, this is not just some variable, it's a very specific amount, half the concentration. So on this side of the equation, we substitute in 1 over initial concentration divided by 2. Substitute that in, and then we can rearrange for half-life like we did here. And when you do that, if you want to try it, you could confirm it, but we get a different expression for half-life. It comes out to be 1 divided by K over initial concentration. Okay, and then for a zeroth order reaction, whose equation is concentration equals minus KT plus initial concentration, substituting in those same things, T half-life, the amount of time required to reach half the concentration, and this is not just any old concentration, it's half the initial concentration. Substituting that in here, solving for half-life again, you can show that for this particular type, the half-life is the original concentration divided by 2K. Okay, so let me make some comments about these half-life expressions. For the first order reaction, I would say this is the most important type to recognize. Questions on the AP exam often deal with first order half-lives. The reason is because this half-life is a constant. Okay? The rate constant is a constant, and the natural logarithm of 2 is a constant. So we have two constants being, the ratio of two constant numbers is itself a constant. Okay? And we just saw that in this problem right here. Every 100 seconds, the 100 doesn't vary. It's always 100 seconds. Every 100 seconds, the concentration's being cut by half. Okay, and that's also clear if you look at the, I mean, we were talking about the data itself, but when you look at the data, right, every 100 seconds, so here's the curve, right, every 100 seconds, that initial concentration gets cut in half, right? Every 100 seconds gets cut in half. So after another 100 seconds, concentration's cut in half again. After another 100 seconds, concentration is cut in half again. All right? And it'll go on and on and on and on forever until it's extremely close to zero, or you're down to that last molecule or atom, and then it has to react as well, or whatever. Okay, so you have a constant half-life in a first order reaction. Okay, that's really, really important to know. First order half-lives are constant half-lives. In contrast, for second order and zeroth order reactions, you do not have a constant half-life. Look at the expression here for the second order one. 1, well, that's a constant. K, that's a rate constant, that's constant. But the initial concentration, okay, that is changing all throughout the course of the reaction. At any given moment, the half-life is changing. At any moment. The amount of time required for half of reactants to react depends on the concentration. Okay? Okay, so this is not a constant amount. Okay, and the same is true for the zeroth order. Okay, 2 and K, those are constants, but the initial concentration of A is changing all throughout the course of the reaction. You know, if you look at a graph and then you pick another particular moment, that's going to impact how much time is required. So same thing here. Okay, and this is kind of strange because that means the half-lives themselves change. Okay, these T subscript 1/2 change throughout the reaction. Okay, but this one right here is constant for the entire reaction. Okay, so in one of the other problems I had you do on your own, it turns out that it's a second order reaction. So on this problem here, I asked you to decide whether or not the reaction's first order or second order, and your instructions were use this data and generate some graphs. Nobody's contacted me so far about needing help with graphing. But I've given you some graphs with this data, and I've come up with 3 individual graphs. So there's the data written out again. It's the exact same data. Time is the x value, though. That's the independent variable. And this is your y values, the dependent variables. So concentration's a function of time. So I've rewritten them x, y this way. Okay, and I've also done the 2 other transformations, I suppose you could say, the natural logarithm of concentration and the reciprocal of concentration. Okay, and I've graphed all of them. Okay, so here's the concentration versus time. Now let's just show that the half-life is changing. This happens to be a second order. It is second order because we've seen that it's the inverse, the reciprocal of concentration versus time, that gives a linear plot. So we know that this is a second order reaction. So we could infer that the rate law would be K C4 H6 squared. Okay, because this is the linear plot. Now, since it's second order, the half-life is constantly changing. So let me just show you that the half-life is not constant throughout this reaction. Okay, so first of all, how much time is required for it to drop from 0.01 to half of that? Okay, so that would be 0.005. So right in here. Okay, and so here's the curve. It would be right about there. Okay, and that amount of time is about, I'll show you in a moment, it is 1633 seconds, I believe. Okay, now let me show you how I figured that out. Okay, for a second order reaction, T 1/2 equals 1 over K initial concentration. Okay, so 1 divided by, what's the rate constant here? Well, we can figure out the rate constant. There it is right there. It's the slope of the linear plot. So 0.0612, and in terms of units for K, we could figure those out as well. Remember, rate has the unit of molarity per second. So what units do K have to have if we've got molarity squared here? Okay, this has to be units of molarity to the -1, seconds to the -1. So our rate constant, 0.0612 molarity to the -1, seconds to the -1, okay? And what's that initial concentration? 0.01. With 4 significant figures. Okay, now look at the units. Molarity and molarity to the -1 divide out, and we've got per seconds in the denominator. And so let's evaluate the numbers. Grab the calculator, pull this over here. We've got 1 divided by 0.0612 times 0.01, everything there in the denominator, 1633.99. With 3 significant figures anyways, you could say 1630. It's about 1630 seconds. Okay, so that would be the half-life, but it's not going to be a constant half-life. So now let's see how much time is required for it to drop, say, from here at 0.005, halfway down to 0.0025, which would be somewhere in here. Okay, so that right there, starting off here, how many more seconds would it take before we hit that curve again? Somewhere out in here. Okay, and notice that is a different amount of time from here to here. This was the first half-life, you could say. You could call that T half-life number 1 or something. I'll just say first. Here's the second half-life, and it's a longer amount of time. Okay, so how much time are we talking about here? So for the second half-life, we would plug in a different initial concentration. This time, same rate constant, 0.0612 molarity -1, seconds to the -1. The rate constant's still the same. But this time, the initial concentration, we're going to use the 0.005. And then how much time will it take to get to half of that? So I'm going to put 0.005 molarity. Again, molarities divide out. We're left with per seconds in the denominator. So what's that half-life going to be? 1 divided by 0.0612 molarity -1 seconds -1 times 0.005. This will give us the second half-life. Notice it's longer, and it's actually twice as long. It's exactly twice as long. Okay, so 3270-ish. All right, I've rounded this one down. I'm rounding this one up. 3270 seconds. And it's twice as long. Okay, look. And so that amount of time that's totally elapsed, that's been the first 2 half-lives. The second half-life is twice as long as the first half-life. If I had drawn these in, well, that'd be a bit clearer. All right, and then if you did the third half-life, it would be twice as long as the second half-life. You'd have to go really far out here, somewhere like in here, before that curve finally got you down to half that concentration. Okay, so the main idea here is the half-life for a second-order reaction is not constant. Okay, the only time you have a constant half-life is when you're dealing with a first-order reactant. So those are definitely the most important, and that's why they include them on your AP reference pages. They've given you the integrated rate law for the first order. Okay, so that's the first order integrated rate law. This is the second order integrated rate law. They didn't even put the 0th order integrated rate law. And they've given you the half-life for a first order reaction. Okay. So let's go back to this problem here. I've actually already answered this. What's the half-life for the reaction under the conditions of this experiment? Okay, well, it's not a constant half-life. And frankly, the best that you could say for C would be, since it's a second order reaction, that it's 1 over the rate constant value times that initial concentration of A. And really I should say, it's not A in this case, it's C4H6. Right, so that would be the half-life of that reaction. You could say the first half-life, was about 1630 seconds, and the second half-life, not the same amount, twice that amount, 3270 seconds. Okay, it's changing at every moment. Okay, so that's a quick lesson over half-lives. If you see a constant half-life from your original data, like if you're looking at your graph and you notice, hey, there's every 100 seconds or whatever, every X number of seconds, the concentration's dropping by half, it's a first order reaction. Okay, and by the way, that's because it's an inversely proportional relationship. If you think about the rate law itself, it's inversely proportional. Oh, the rate's inversely proportional to if you got rate here. Sorry, the rate is directly proportional to the concentration. Okay, and so in terms, but there is an inverse relationship kind of hiding in here, and that's with time. Okay, so the concentration and time have an inversely proportional relationship. Okay, and all right, so with that, that finishes up the lesson for half-life. So message me on Zoom if you would like to set up a meeting. Otherwise, you have your last assessment before spring break on AP Classroom. You can locate it there. It's due Friday night at midnight.